Okay, welcome everyone to our presentation today. This webinar is on vibration control as the main topic. My name is Bill Flynn. I'm application engineer with Siemens out of the Siemens Cypress office down here in Southern California. And I'm joined by my colleague, Charles Rice, and I'll let Charles introduce himself.
Hello, everyone. My name is Charles Rice, as Bill said. I'm also an application engineer working on the West Coast for Siemens.
Great. Thank you, Charles. And this is the agenda for today, the vibration control introduction, the what, why, and how. And we'll go into a little bit about the self-check and the importance of a self-check and a good quality self-check. Talk about random control testing. And those are the topics in our agenda for today for this webinar. We also have a subsequent webinar later on today that you're welcome to join too. So first of all, the introduction with the what, why, and how. Environmental testing, basically environmental testing, it is broad focus, and environmental testing can be not only our focus in the subject today, which is vibration and acoustic environments, but it also includes many other different types of environments, and this can be salt, fog, temperature, humidity, things like that. So basically you want to replicate the environmental conditions that your product would see in operational conditions and replicate those in a laboratory environment. And that would mean either replicating or characterizing through some frequency response measurements. And those are based on vibration testing, vibration or shock testing in the form of random, sine, or shock, just depending on what you want to replicate and what characterizes the best that the environment that your product would be subjected to. We want to actually go out and measure these and either replicate or characterize these in some way and bring those into the laboratory. We want to do that through either shaker excitation or maybe even acoustic sources. And typically this is in a closed loop type of control mode. So that's what the environmental testing is
Bill, I
about.
had a quick question. If we could go back a
Yeah,
slide.
Charles.
I saw three profiles on there, random, sine, and shock. Would it be possible to combine these profiles? Like say, for example, someone has a product that has a strong sinusoidal component, but also high levels of random vibration?
Yes, that's a good question. Yeah, so that is what we call sign-on random. So that's a good application for that. Environment for that would be like in helicopters. So they have a strong sinusoidal type of component superimposed on a random background. For tracked vehicles, for example, those would have sometimes a narrow band random on a broadband random background. So the answer is yes, we can combine those different environments in the laboratory, and there's different control modes for accommodating that.
Okay, great. Thanks.
Sure. And any other questions that you have, just feel free to bounce those off me,
Okay,
Charles.
I'm not shy. I will.
Okay, I appreciate that. So when we talk about environmental testing, there's a lot of different types of environmental testing. And these are characterized based on what the goals of the test might be. In spacecraft testing, we talk about qualification testing, acceptance testing. For automotive, there's endurance testing, environmental testing. For example, functional testing, where you may have some electronic components that you want to actually make sure that they operate during the vibration test, for example. And so that's classified as more of a functional test. So there's many different varieties of these different tests for environmental testing. So why perform environmental testing? Well, basically to validate the reliability of the products through controlled and consistent testing, but we want to make sure that we're replicating those conditions accurately. And we want to expose any design flaws. Did it fail? If it did fail, why did it fail? And if it didn't fail, we want to make sure that we understand that we're characterizing those environments accurately. You don't want to be under testing, and you don't certainly want to be over testing. So you want to be accurate in the way you represent those real conditions. So we want to also produce some equivalent lifetime damage contribution, and that leads us to the idea that we can actually shorten the amount of time if need be, just based on damage contributions. We can reduce the amount of test time, for example. And we also want to be able to show that we can improve, maintain quality. So we don't want these products failing when they get out into the field. And that can lead to some warranty issues, also some liability issues. So we want to maintain our reputation through good quality testing in the laboratory. Another outcome of environmental testing could be validation of a digital twin, where we have a computer model of a real prototype structure, and we can also use environmental testing to validate this so-called digital twin. And again, we always want to question the test specifications to make sure that we're adhering to some realistic conditions.
Well, according to the test specifications, with regard to pass or fail, is it just that does the product survive? Is that kind of how we quantify it?
Well, sometimes you got to make sure that you understand what the failure mode is. And yes, so that is something that we want to validate through testing and make some determination whether it fails or passes. Did I answer your question
Yeah,
with that,
yeah.
Charles?
So it's not just if it survives, but you're saying like a functional check afterwards, like if the electronic components still function correctly, even though it's not broken in half, the circuit board or something.
That's correct. Yeah. So it depends on what you characterize as failure and what the failure mode might be.
Okay.
So there's different ways of determining whether a product fails or not. And that's usually the goals of those different types of tests, like a functional test, for example.
Mm-hmm.
Those different types of tests have different goals in mind, and subsequently different failure modes too, perhaps.
Okay. Makes sense.
So when we talk about product reliability, well, this is an example where we have not maintained product reliability. And when the product gets out in the field, we don't want these kind of things happen.
That's very interesting. I guess that's the case where two wrongs made a right, right? It didn't travel very far, but it also didn't explode, thankfully.
Well, that's right. There was, I guess you could say, there's two failures in that example there.
Thankfully, thankfully.
Yeah. So this is kind of depicting where in the whole development process you might want to consider doing your testing and where it's most optimal. So certainly when the product's out in the field, you don't want to be testing and finding out about failures when it's out in the field and doing troubleshooting at that point. You want to bring the testing back into the development process a little bit further back. Here in the concept stage is where it's mostly based on computer models. So there's no real structures to actually test, but you can do as much simulation as possible there. And then once you have some components that are available for testing and to validate with models, that's where you want to do some testing. And then subsequently up into the subsystem level, and that's where you can do some testing there, environmental testing. And further along you get in the development process, of course, if you look at this graph over here, this axis, the cost of change goes way up exponentially, and the ability to change goes way down. So of course you want to expose these design flaws early in the process, bringing down costs of change. There's different industries, and a lot of different industries, many different applications and industries rely on environmental testing. A lot of times the companies don't have the resources in-house, and so they have to outsource the testing, and it just depends on the situation and the resources and funding that's available within a company, whether they would do this kind of testing in-house or they would outsource these to some test houses. Many different industries and different products rely on environmental testing, of course.
What are the major pro or con versus in-house or outsourcing this vibration testing?
Well, again, I think, Charles, it just depends on the situation, the resources that a company may have. These systems, these shaker systems and vibration control systems are expensive to maintain sometimes. And there's a lot of resources that goes into that, not only maintaining these and the financial resources that are required for that, but also the experts that are used to run this. You have to have people internally and support those people internally as employees, and that's a lot of cost involved in all of that.
They have to pay somebody like you, huh?
That's exactly
and
right.
They're not cheap,
and that's right. I ain't cheap. So you get the idea. Kind of depends on the situation. In some cases, it makes more sense for people not to have these resources internally, but to outsource those to external test houses.
Yeah, makes sense.
So as I said before, environmental testing, that pretty broad scope term, environmental testing, it can involve many different types of environmental tests. How you go about these types of tests, they're all described in these different test standards that I'll mention here in a minute. And they're all pretty well defined in the test standards and many different types of tests for environmental testing.
Yeah,
But of course, we want to focus on the dynamic testing.
that's good. I was wondering, I didn't see vibration testing on the list, so
I characterize vibration testing and lump it into dynamic testing because that involves time waveform replication, vibration testing, random testing, sign testing, but also shock testing.
okay,
I would say that's a dynamic test too. So it's all kind of contained within this dynamic testing title here.
gotcha.
And combine these sometimes too, like temperature and humidity in test chambers that include vibration and temperature and humidity. So that's also a test that's done too, where you combine these different environments.
Okay.
This is a list, sample list of all the different standards that are out there and available. Of course, I think the most popular, I think the most common one that's used, and again, it depends on the industry that you're in, but generally speaking for military standards, it's the MIL Standard 810 is the most popular and most frequently used, and it's a very comprehensive document that covers many, many different types of environmental tests. So it's not only vibration and shock, but also many other different types of environmental conditions.
Is that the
And
toughest
then
one to pass, you think? The MIL Standard 810?
I wouldn't say it's the toughest one. They're just different flavors
Okay.
and different requirements and different goals for these different standards. Some of these could be considered more difficult than the MIL standard,
Mhm.
but just depends on the situation, the application, and the industry. And there's others like the ASTM, American Society for Testing Materials. People will pick and choose based on their product, which one is more applicable to their product and which one they would use. So in automotive, these ISO standards are probably more common in the automotive industry, whereas the MIL standards are more common in the aerospace industry.
Mhm.
And there's other standards that are for other types of applications and industry. And it's not only in the U.S., but of course Europe has and Japan has their own standards that they've tailored for their requirements too.
Okay.
Just taking, for example, the MIL standard, this is a little bit of history. Back in the World War II, things were breaking in the field and they wanted to mitigate that and reduce as much as possible things failing in the field. So they had to come up with these test standards. And if you wanted to submit your product as a proposal to the military, you had to make sure that you adhered to their particular standards. And so they started to evolve and develop these standards way back in the 40s. And the MIL Standard 810 has evolved to the latest document, which is in January of 2019. And it's evolved from 71 pages almost up to 1,200
I
pages.
see where my tax
So it's
dollars are going, Bill.
that's right. Yeah, a lot of effort has gone into developing these. And of course, it takes a lot of resource and a lot of money to develop this standard. That's one of the more popular ones, and especially in the military industry, I'd say. So now we get into the how. We talk about time waveform replication, sinusoidal type excitation, random excitation, and shock excitation. Whatever is applicable to your product and what it's exposed to and its operational conditions, which one is more appropriate. And these are all based on different frequency ranges. Like the time waveform, that's typically higher amplitude, and then we get into the sinusoidal, a little bit higher in frequency. It's more common in the spacecraft industry. And then we have the random and acoustic, again, just depending on the frequency range that you want to cover, and the shock covers a higher frequency range.
Okay. Is there any, I'm just
Mm-hmm.
noticing the order there and different amplitudes. What, for example, if I needed to do sine and shock testing, is there, I have to do the sine test before the shock because that sine general had a higher amplitude there or the test levels?
It really doesn't matter.
Okay.
I mean, let's take, for example, a spacecraft test. They would probably do a sign test and a random test, and they would also do shock testing. And the order of that really doesn't matter too much.
Okay.
They have a standard to adhere to, and if they've kind of let's say, check that box, that they've adhered to the standards and done a sign test, they could do the random test after the sign test or the random test before the sign test, whichever fits their scheduling. So as far as the sequence, it really doesn't matter too much, generally speaking, I'd
Okay.
say.
I'm not going to hold you to it, but this is being recorded, Bill.
Oh, okay. All right. Well, I appreciate you letting me know that, Charles. So again, based on, the type of test, it's kind of based on this stress strain curve, or let's say the SN curve. This is the stress level versus number of cycles, and we have this SN curve. And right in here in this blue area, in the elastic area, that's where if you stretch something, a material, it returns to its original form or shape. And in the plastic region is where that's not the case. If you stretch it too much or stress it too much, then you don't have exactly the return to the original position, and that's in the plastic region. So you don't, of course, want to expose your product or have your product exposed to this type of excitation too often. That leads to a higher level of damage and higher probability of failing. But you've also got some amplitudes of vibration and stress levels that are kind of characterized, well, let's say they're in the infinite life. So no matter how many cycles of this level of stress you expose it to, it's never going to fail. That's in the infinite life range. And we can utilize that information through a measurement of this time history of the product, and we can filter out the cycles that contribute to infinite life. And then we can base all of these cycles on this SN curve. And in the elastic region, we can use that information to shorten test. We can base that on what's called the damage, and that's all according to the Miner's rule. And then how we go about testing, well, there's different types of tests, whether we want to use sign control, random control, or shock testing. Then also we want to consider whether we want to use a frequency domain environmental vibration test, or we want to use time domain, whichever one makes more sense. In this way, in the frequency domain, we characterize those response signals, and we can characterize those through some frequency responses. And depending on the frequency range that we want to cover, that would dictate whether we use random sign or shock test, or as you mentioned before, Charles, we can even combine these different modes like a sign on random type test. These can be based on real measured data, or they can just be cookbook type of spectrum characterization based on some mill standards, and those are very well defined in those mill standards, for example, and we just take that spectrum and apply that and the rules in applying that spectrum in our vibration control test. Then in time waveform application, we're taking the exact time history and we're applying those in the time domain to our system. Then another consideration in what type of test, we either want to do single axis, multi-axis, and this can be 1 degree of freedom, it can be 3 degree of freedom. Here it's a 3 degree of freedom test. Here it's a 6 degree of freedom test where we're actually taking into consideration the rotational degrees of freedom too. Of course, the sophistication of these different excitation systems get to be quite high. This is a 4-poster system for automotive industry, and typically we use time waveform replication for those to replicate the responses in the time domain. Here, this what we call a team cube. So this is actually inducing some rotational responses. And then we have a 3-DOF shaker system that we want to use for 3 degree of freedom vibration testing. And then typically, and probably the least sophisticated system as far as the hardware goes and also the control algorithms, that's in the single degree of freedom test. So now we talk about the self-check and the importance of a self-check. So basically this is a measurement of the system transfer function where we're measuring the voltage output and measuring some response back. We want to use this to ensure the integrity of our entire test setup, including all of the hardware, including the amplifier, the shaker, the response of our sensors. So all of this is taken into account in our self-check. And basically it's a system transfer function measurement. Whether we want to consider this as a closed loop, and just to distinguish between the two what we mean by open loop versus closed loop. Of course, for our environmental testing that we are thinking about today, we are thinking about closed loop, where we have some responses after sending out some excitation through our amplifier to the shaker and exciting our structure. We have some structural responses, and we have those reference spectrums here that we want to adhere to. So that's in a closed loop fashion, but we can also do some measurements over here, maybe some monitoring channels or some other channels like strain gauges or temperatures or things like that, that also we might want to measure as we're controlling this to, again, expose our structure to those kind of environmental conditions and measure responses around the structure.
Phil, so
Yeah,
looking
Charles.
at the open loop, like it mentions there on the slide, like shows for modal and ODS, so many times, we get FRFs out of there, we can get some mode shapes. But the closed
Mm-hmm.
loop, is it often that you also measure like operational deflection shapes or even put some force transducers and get mode shapes directly?
Yeah, kind of the main objective here, Charles, to ensure the safety while exposing it to this reference spectrum.
Hmm.
As a side benefit to this, these measurements here, you can also either, if you're measuring the force going into the system, or if you're just measuring some response signals, you can use that information as input to operation deflection shapes. As an added benefit to a closed loop control test, you can use that for this application of operation deflection shapes, ODS. And you can also use that if you're not measuring the forces, then you can use this for operational modal analysis too. So that's a possibility.
Okay.
And then you can use that for comparing to your finite element model predictions too, and validating your digital twin that way. So
Okay.
some added benefits to a vibration control
Yeah, that
test
closed
are
loop, you kind of get your
possible.
cake and get to eat it too.
That's exactly right.
And you need some
Yep.
more channels, and we're big fans of increased channel count here.
You betcha. Yeah. More channels, the better, huh?
And that's what I say.
Yeah. So, yeah, and a fundamental difference between those two, the open loop and the closed loop, is with the transfer function that we're measuring. So typically with measuring the forces and the responses of the accelerometers, we're using the transfer function acceleration over force, which is commonly called the frequency response function. Whereas in vibration control, we're measuring the so-called SysID, which is the voltage output from the DAC, and measuring the responses, and that gives us our G's response per volt output. And we do that because we need to derive a closed loop form of the output response spectrum or output spectrum to the shaker. And we do this by inverting that transfer function or SysID. So we want to make sure we're very accurate with that because we're going to use that to calculate our voltage output to the shaker. So you don't want to be too high, but you want to make sure that you maintain a voltage output that maintains this response spectrum of your control signals. And it's kind of like an audio spectrum, an equalizer, what we call it. So the controller has the job of adjusting these dials up and down to maintain a certain reference spectrum, and it does that in closed loop fashion automatically.
I got a question on that last slide.
Yeah, Charles.
So we talked
Sure.
about the SysID. You said needing to be very accurate, right?
Uh-huh.
And then at the bottom there says we need to update this drive signal constantly. Why would I need to update
Mm-hmm.
it if I measure it accurately first time?
Well, that's a good question because typically we're measuring this, and through a self-check, we're measuring this at a low level. You don't want to be jumping up to full level right
Hmm.
away. You want to kind of build up in levels, but that also introduces nonlinearities or nonlinear responses. So we want to make sure that we adhere to this level, but to the reference spectrum
Hmm.
prescribed level as we step up through those levels. But as we step up in level, we're going to have changing conditions and changing responses,
Okay.
which basically that's considered a nonlinear response. And so we want to make sure that it's closed loop form so that we can accommodate for any nonlinear responses.
That makes
And
sense.
things fail during the test too.
That's true
So
too.
if something fails, you want to be able to monitor that and not keep outputting to break your part even further.
Makes a lot of sense. Okay, got it.
Mhm. A quality indicator of transfer function is through this coherence function. This is the calculation of the coherence function, and it gives us a value from 0 to 1. 1 is perfect, 0 is no good. That means all the response that you get in a particular frequency is not due to the input going into the system. When it's a value of 1, that means the response that you get out of the system is completely 100% due to the input going into the system. And that's a perfect coherence. You want to be as close to 1 as possible, and you can measure that through the coherence function. As you build up in drive level, this is the sequence of events from the self-check. So you start with basically no excitation to measure the background noise in your system. And you want to have that as low as possible, of course, but sometimes there's extraneous noises and maybe some electrical noise that you want to measure also. You don't want that having too much influence on the signal that's being measured. So you want to measure the background noise, and that's also used in the signal to noise ratio calculation further down. And so as you build up your level in self-check, you get to a minimum drive level. Again, these are much lower than the test level, and you just want to, let's say, tickle the structure a little bit to get the initial measurement of the transfer function. And it's using that information to extrapolate up to full level. So this is a complete end-to-end check of your entire system from the voltage output to your response all over the structure, including not only your control sensors, but also any measurement sensors that you have. You can also measure those too and characterize those as far as signal to noise ratio. And so it's very important to get a good self-check.
So let me just summarize to make sure I understood. So with
Yeah, sure.
with the self-check, basically we're testing at the lower level just to be able to predict the performance at full level, right?
That is correct.
Okay, so this predicts the future. Can it predict anything besides levels, Bill? Because we could use that. I'm just joking.
Okay, so like predict your future, you mean, Charles?
It's not so great. That joke didn't go over so well. So let's go on to the next slide.
You'll have to run your own personal self-check. So this slide gives a summary of what comes out of a self-check. Very important function here that may not be so popular, but very useful in some cases is this digital scope. So you have two tabs here, the self-check, and then you have digital scope, and you can use this digital scope to diagnose problems, perhaps, that if you have high background noise, you can determine by spectral response whether that's due to electrical noise. You can actually test your sensors by looking at the response. If you tap on the structure, you can look at those in the time domain. Then also, as a result of the self-check, you get any error messages. You get an overall global status. Basically, it's an end-to-end, very comprehensive check of your entire test setup. Very important. And these are some sample results that may come out of that. As I said, you get a global status, and in this case, it's an orange message, which is a warning. Sometimes if they're orange, it's just a warning. If it's a red, then it's not to proceed type of error message. So you have to rectify whatever problems that you're getting that message from until you can proceed with the test. There's a lot of checks that go on. There's a loop gain, which is basically an end-to-end transfer function. So it's an RMS of your Gs versus RMS of your volts output. And that's a pretty consistent value there. So depending on the gain setting of your amplifier, this should be pretty consistent. Then also you get some information about the drive levels. So in this case, it was outputting 30 millivolts to the shaker and amplifier, and then it can use that to extrapolate up based on this system gain, the loop gain. You can use that to extrapolate up to full level to make sure you're not going to exceed any levels of your drive output, that your system is capable, that you've got your amplifier turned on, for example, and you've got enough output from your DAC output to accommodate the test requirements and the levels that you need. As far as the control channels, you get, again, the quality check of your transfer function. You want to have this as high as possible. Don't want to have a minimum coherence that goes below a certain level because you're going to be inverting that transfer function. So even the peaks and valleys of your transfer function, even the valleys are important. So you want to have good excitation, good response, and have your transfer function, and that's all indicated through this coherence function.
Bill,
Yeah,
when I look
Charles.
at the self-check results, I'm noticing one thing. I mean, I haven't used the vibration testing software as much as you have, certainly. But I noticed the minimum level seems a little bit higher than it I normally use when I just turn on the software, the default value. Is that
hmm
kind of a recommended?
This, yeah, this down here. So, out of the box, the test lab software is always going to be very, very conservative. So I think it comes out, the minimum default value is 5
That's what I
millivolts.
see, yeah.
Well, a lot of cases that's just in or just above the background noise. So again, you want to get, and I think the maximum is 20 millivolts. So those are pretty low levels. So again, pretty conservative. So this is my
Okay.
default that I use, a 20 millivolt minimum, 60 millivolt maximum. And then you're going to have a number of steps,
Okay.
let's say 5 steps to step up to full level. Yeah, you're right. Those are minimally, that's probably, if you've done vibration control test out of the box, that's kind of those are pretty low levels. So you want to kick those up a little bit to get a good transfer function, which means you'll also get good coherence values.
Okay.
And in fact, typically I would just look at these. That's a good indication of a good quality self-check, good system check, looking at coherence values.
Okay.
A lot of things can go wrong in a test, and it's really up to the controller to help you to watch out for these things. And that's why it's such a comprehensive test. A lot of things are being checked by the system automatically. For example, overloads, open channels, DAC issues. So if you forgot to turn the amplifier on or turned it up too much, a lot of these things will come out of the results of a self-check. If you got too high of ground loops, if you've got a sensor that fell off, all of these things should be discovered from the results of a
I
self-check.
can vouch for this. I've done quite a few of those on the list.
Yeah, yeah. You've come across a lot of
Yep,
these.
those are
And
all true.
And these are some very common self-check errors, and I just wanted to show these with a few examples. And the DAC overload, the control response overload, open channels, and this obscure one that comes up every once in a while for customers, this excessive DC level or DC variation. So I just wanted to mention those. And these are covering some of the common errors that come up from self-check. What I've done is given some examples here and the outcome of these errors and what settings produce these errors. And then also what's more important is what can you do about these, and some background information about how they happen and why they happen. There's thresholds here, for example, and you get a DAC overload. What do you do about that? Well, a lot of cases someone hasn't turned the amplifier on, so you're trying to extract too many volts out of your DAC output. And if your amplifier is not turned on, then it's going to give you a DAC overload. Or if your test levels are too high. So with this type of test, pretty high level test, 11.6 GRMS test, we got a max drive output of 9 volts. So we can use that information. That kind of sets our threshold. So based on the sigma setting, that's part of the setup, we have a max threshold or a threshold. So if you're over that, then you're going to get this error message DAC overload. And in this particular case, we have an 11.6 G RMS test, and we have a system gain here of 3.711. Well, that gives us a voltage output requirement of just slightly over our threshold of 3 volts RMS. So that's the reason that we get this DAC overload. So this is what it's using based on the low-level prediction of self-check, the transfer function or loop gain. It's using that to predict what we'd get at full level. And then here in these slides, I also put down here things that you can do to overcome those errors. So it gives you some ideas of how to overcome these errors. And then I won't go into a lot of detail here, but this is another example. If you get a control channel overload, well, these are red messages, so you're not going to be able to proceed with the test until you determine what's causing these errors, why, and then rectifying the reason for those fatal errors, or let's say those errors that prevent you from continuing on with the
Yeah,
full
yeah, they're not
test.
gonna die, hopefully.
That's right. That's right. So you get the response overload threshold, and that's calculated with the sigma factor and then an extra safety margin that is used in the calculation of this max voltage response. Based on the transfer function, it's predicting up to full level and calculating a 24G RMS test using the sensitivity of that sensor, which is 100 millivolts per G. It's going to predict a 2.4 volt RMS requirement, and we're over that threshold of 2.36 just slightly, so it's going to give us this overload message, and it's going to stop you from proceeding with the rest of the test. And then what you can do about that, some ideas on that. So then also an open channel is pretty common, and how they occur. There's a couple cases where the open channel can occur. Very simply, in a self-check, you've got this signal to noise ratio. So again, it measures the signal that it's measuring, and then it measures that background noise and calculates that ratio of signal to noise. And if it's not over this factor of 20, which in this case it was 17, so there wasn't enough signal to overcome the signal to noise ratio, so it gives you an open channel and you are not able to continue on. So those are the things that the system does to help you to determine automatically any issues of your system and checking the integrity of your entire test setup. And then if you have an open channel, what are some of the things that you can do about it? We also have these common self-check error, this excessive DC level. Many years ago, we allowed to have strain gauges included in a control system. Well, strain gauges are typically DC level measurements. We want to accommodate that in a mix of strain gauges and accelerometers. And so we're going to allow a DC offset with a strain gauge, but now with the accelerometer, an ICP type, IEPE type of sensor, those should not have any DC offset because they're AC coupled. So if you do have a DC offset, then that indicates a problem. So we want to measure that DC level, but with strain gauges, we're going to allow a DC offset, but we don't want any of those channels to vary too much in that DC level. So that's what the DC variation is, and we can make those kind of checks. And if we exceed those thresholds, then we get this excessive DC level. And the thresholds are determined by the settings in the advanced self-check parameter settings. And how they occur and why they occur, well, this is measuring this settling. So as a function of time along this axis, it's measuring this DC level, and you can see it's kind of settling closer and closer to zero. But eventually, and if you had zoomed in on this, you'll see the variation exceeds the threshold of 10 millivolts, and so it did not allow the continuation of this test and gave this excessive DC level and background noise error message that doesn't allow you to proceed with the test. And again, you can use, back in the self-check, you can use the digital scope to try to see what might be causing that problem. So that's a little bit of background on the excessive DC level. Then we'll go on to random control testing and some of the parameter settings for that. And again, for random control testing, we're in this frequency range here. And as I've mentioned before, we have this random control spectrum that's used for the closed loop control. We have this level, and you want to be as close as possible to that level, and you don't want to go outside. And if you do deviate too much within some tolerance, then you want to be able to have the control system in a controlled manner shut down the output to that shaker. So you have this envelope of the operational environment. The spectrum can be derived from operational conditions or again from those mill standard and a cookbook reference spectrums. The algorithm is shown here. So we go into closed loop control mode. Basically, we have what's called the inner loop and outer loop averaging, and we'll mention those and talk about those in a little bit more detail here. But all of this is done very safely as closed loop control is done. There's a lot of safety checks that are going on in the background. So first of all, we have this so-called inner loop, which is shown here. So this is the inner loop averaging, and this is random data, so you want to do a certain level of averaging. And that's all done in the inner loop inside the data acquisition hardware, inside the DAC. So because of efficiency, we want to be averaging as quick as possible. So we do that in the acquisition system. So that's done with stable averaging, and we take a number of averages, and then once we take those averages, then we go out into the outer loop averaging, and here it's done exponentially on the host PC. And this is the kind of a display that you see. So you can actually display the inner loop averaging, and you can display on top of it the outer loop averaging. The hashy signal is less number of averages, so the random signal is going to be very hashy. And we have outer loop averaging where we're averaging the inner loop, and that's what we consider the average control and what we're trying to maintain to. Then we have another parameter that is part of the parameter settings is the frequency resolution, and this has a strong influence on the loop time. We have to have at least 1 over delta F. That's going to be the time for one single average, and then we have a number of averages, and so that's going to dictate our control loop time approximately. That's the minimum, but there's going to be some extra fixed overhead that contributes to that averaging time too. Then we have number of averages per loop. We do stable averaging there, and then we have some examples of increasing the number of averages per loop. So we want to be responsive, but we don't want to take too many averages, but we want to be responsive to any changing conditions. So one average per loop is probably not enough. It's random data, so we want to take a few more averages, but we don't want to take too many because we get less variation. We also have this parameter that's part of the test setup that's required by the test requirements, what we call a degree of freedom. And that's based on the number of averages and the average weighting factor, which is introduced here. And I'll give the equation for the degree of freedom, but it's based basically on the number of averages in the inner loop and this average weighting factor for the exponential averaging. The exponential weighting factor weights the averages in the previous averaging, and if you have a low weighting factor, then the previous averages have little influence on the current average, whereas the high average weighting factor, the previous averages have higher influence on the current average, and the equation for exponential averaging is given here with this weighting factor shown here. So if we look at how that affects the control, you can see that here, the average weighting factor, a weighting of 1, we're not going to influence the current average with the previous averages very much at all. Whereas if we increase the weighting factor, then the previous averages have a much higher influence on the current averaging. And again, it has to do with the required response of the system to react to any changes that might occur during a test. And here's that degree of freedom factor that's used or calculated based on the weighting factor and the number of averages. That's a lot of times part of a test specification, and people will dictate the number of degrees of freedom, and you can input that directly, and it'll maintain the number of averages per loop in the stable averaging and modify or adjust the weighting factor based on your degrees of freedom. So there's 3 parameters that go into the definition here. So now we'll just go into a demonstration of the random control and the influence of those random control parameters. So this is my test setup. I've got a modal shop shaker with a built-in amplifier, a nice compact, easy setup here. I've got a flat plate with a control sensor, and then I've got a cantilever beam with the number of responses. In this case, I've got a load cell. I can measure the forces going in, and so that's my test setup. The acquisition system that I'm using is shown here. The sensitivities of the sensors are shown here. This is my DAC output going to that modal shop shaker. And then I can also measure the status signal or the COLA signal based on a random or sine sweep test. And then I've got 8 channels that I'm measuring simultaneously along with the control. So let me break into my demonstration here.
Okay, I love demo time.
So demo time, and it's all exciting, always exciting since it's a live demo. So I've got, in this case, my stable averaging, averages per loop is 5. I've got a very low exponential weighting factor, which results in a degrees of freedom of only 10. So we'll see what influence that has and how the control works with that. First, I have to run the self-check. So I'll show the self-check procedure here. Notice I've got a minimum here of 10 millivolts and a maximum of 20. So I think I had steps of 4. So you see the first RMS level is 15 millivolts, and it made it to the first level, and my signal to noise ratio was over the threshold. So it continues on. It met the minimum requirement, and it met the signal to noise ratio. I have all okay channels. I get a global status of warning because of this open channel, and I'm not measuring anything on that. I'm actually measuring the status signal coming out of the DAC, and that's why it's an open channel. So if I go to arm the system, initializing, this is when it establishes communication with the hardware, and so I start the test, and we'll see the influence of those settings. Now right now I can see I'm exceeding the abort lines. I've got 12 and my threshold is 5, but it's not shutting down the test. That's because I'm not going to allow it to shut down until I get over at the 3 dB level. So at -9, -6, and then -3, I'm not going to allow it to shut down until it gets to the -3, even though I'm way exceeding my abort lines. So now if I step to the 3, it should abort, and yes, it does. So I've got max of 5 allowable abort lines, and I've got 7 abort lines. It'll stop the test. We'll stop that, and then let's go change that setting, and let's change this to 120 degrees of freedom and just see what influence that
I got a
has
good feeling about
on
this
my
one.
control. Think this will
I
work,
got a good
Charles?
feeling about this one.
I think you're predicting things correctly there. Yeah, because 120 that's a pretty standard value for degrees of freedom. So you see the inner loop averaging is getting better and better and better because we're taking into account, we're weighting those previous averages. And even when I step to the next level, you can see it's starting to average with the previous averages with much higher. So step to the next level. So it's resetting the averages when I step up to the next level. But my outer loop averaging, this PSD average control, it's well within the tolerances, so I'm able to step to the next level, and I'm not getting any aborts at all in this case with a much higher weighting factor. So I can continue all the way to the end of the test, but in this case I'm going to stop it and go back to the presentation mode. And with that concludes the webinar. If anyone has any questions to follow up with this, we can certainly follow up, and you can send me an email.
Thanks, Bill. Appreciate it.
Okay. Thanks, Charles. Thanks for your help.